All right, so chapter 7, part 5. Let me export this before I close it. Okay. All right. So chapter 7, part 5 is about parametric equations. Now, you might have seen this on your calculator when you were fiddling with it, and you go to mode. We change radian to degree quite a bit. You might have seen this func, pair, pole, seek, and wondered what the heck that crap is. Well, it's different ways to graph relationships, and today we're going to discuss that one, parametric. And we'll eventually be changing our calculator to that mode, so be ready for that. Okay, so we're going to graph parametric equations, and they're very good for modeling projectile motion. Because if I just do it in terms of x and y, I'm missing a very important factor, that is time. So the time an object takes to travel is very important, and it's not possible to represent that with just the x and y path of the object. So if we introduce an additional parameter, usually t for time, it incorporates that extra information. So parametric equation is one where x and y are related to t. Parameter, is this a variable? Orientation is the direction. So with respect to an xy curve, direction is moved. But with a parametric curve, it will have a certain direction. So we're going to have to put little arrows on the graph to indicate that. I'll show you how that's usually done. And a parametric curve is just a graph of a parametric equation. Questions about anything? Make sure I don't leave you in the dust here, guys. So with the parametric equation, you're going to have x equals some function of t and y equals some function of t. So that's the way they're typically represented. Here we've got one. X equals t squared minus 1. Y equals t over 4 plus 2. So both x and y are an equation dependent upon t. And we want to graph it on the interval from -3 is less than equal to t is less than equal to 3. So we're going to create a little table. You remember how you used to do this? You remember this from? Of course, you just did this bit. But now we're going to do this bit. So -3, -2, -1, 0, 1, 2, 3. Your calculator can do this for you, okay? But we're going to do this one by hand just so that we understand the process better. So -3 plugged into this expression, -3 squared is 9, minus 1 is 8. And then -3 over 4 plus 2. Well, remember that 2 is also 8 over 4. So -3 over 4 plus 8 over 4 is positive 5/4. And then -2 squared is 4, minus 1 is 3 for the x. For the y, -2 over 4 plus 8 over 4 is 6 over 4, or 3/2. -1 squared is 1, minus 1 is 0. And then -1 over 4 plus 8 over 4 is 7/4. 0 squared minus 1 is -1. And then 0 plus 2 is 2. 1 squared minus 1 is 0. And then 1 over 4 plus 2 is 9 fourths. 2 squared minus 1 is 4 minus 1, or 3. Notice the quadratic symmetry here with the x's. And then 2 over 4 plus 2, 10 over 4, 5 halves. Yep. And then 3 squared minus 1 is 8. 3 over 4 plus 2 is 11 fourths. Like so. So if we graph this, think about the x's and y's we need. We need the x to go -1 and then out to 8. We need the y's to go, let's see, this is fairly close to 3, and then the smallest one, a little more than 1. So let's do this, 1, 2, 3. Like so. Now we'll plot our points. First of all, 8 and 5 fourths. So that's something like this. And then 3 on the x and 1.5. 0 and 7 fourths, so real close to 2. -1 is at 2. And then back to 0, and we're at 9 fourths. Back to 3, and we're at 5 halves, which is 2.5. And then back out to 8, we're at 11 fourths, which is just less than 3. So if I graph this, it's going to look like so. But I need to add these orientation indicators, because this one also has direction. So we see it's a sideways parabola. Let's graph it on a calculator and make sure it agrees with what we've got here. So be prepared to do this. Go to mode, change from func to par, and then hit y equals. Notice you got a different interface here. To get the old interface back, you need to go back to func. Mode changes the graph from func, F-U-N-C, to par, P-A-R. Hit enter. So x is, notice if you hit the x button, that becomes t. So t squared minus 1. And then down here, t over 4 plus 2. And if we go to our window setup, we want to go from -3 to 3 on the t. And looks like the graph is okay, the default graph. Okay, good. Now, you can't see the orientation unless you have it graphed pretty slow. Let me show you how to do that. See this t-step? The smaller I make this, the slower it will trace out the graph. So if I make this, I don't know, it's 0.13 now. Let's make it 0.05. See how it's slower? I can make it 0.01. Now look how slow. Oh yeah. Take your time. Despacito. 10 more time around that vertex. Well, that's an ugly graphing. Not a great job, TR count. Okay, questions about that? Parametric relationships, where both x and y depend on t. Now, you're used to what are called rectangular relationships. Maybe you don't know about that term. That's the type of graphing you're used to, is rectangular graphing. That's where x depends on y or vice versa, and there's no t involved. Parametric is when you have a t. So rectangular is the standard graph that you're accustomed to. Parametric is this new style. Okay, so we can go back and forth between those two representations. So we're going to rewrite this in rectangular form. We want to get rid of the t, cast it out. And so there's some algebraic tricks we'll employ. Usually you want to take the one that's easiest to solve for t. And I identify that this is the easiest one to solve for t. So I take y over 2 equals t, and I'm going to plug that in for t in the other equation. So whichever one's easiest to solve for t, solve it for t, plug the resulting expression in for t into the other equation. So the result is x equals y over 2 squared plus 2, x equals y squared over 4 plus 2. And, you know, there's a lot of different ways I could write that. That's a conic section. So if I wanted, it's a hyperbola, I believe. So if I wanted to write it like a hyperbola, no, actually it's a parabola, isn't it? Yep, so I have to multiply through by 4. And then I'd have to subtract 8. Then I'd have to come over here, do this. There we go. Now it's in standard form. But this is the answer I'm looking for on the test. I didn't make you go this way. Just as soon as you get it solved in rectangular terms, just compare your result to my answers and you'll find one that matches it if you did it right. Questions about that? So that's moving from parametric to rectangular. From parametric to rectangular. Okay. Now, so this is moving to rectangular form with domain restrictions. I'm not throwing one like that at you, but I'll just discuss it with you real quick. You've got to be careful. You see how certain values of t wouldn't be allowed? Because here it would cause negatives under the root. Here it would cause division by 0. So you would have to consider that in the final form. I didn't throw one like that at you, but it's just something to be conscious of. The potential for it exists. So, spoiler alert. A good throw, wasn't it? Okay, so this is moving from rectangular form in terms of, well, actually, this is parametric with theta as the parameter. So from rectangular form with theta, so parametric with theta to rectangular, where no theta is involved. So this time, instead of eliminating t, we're eliminating theta. And eventually I get it out properly. This is going to be tricky because, I mean, can we solve that for theta? We can, but it's going to have a sine inverse. It's going to be a mess. If I try to plug that into this one, the cosine and the sine inverse aren't going to play together very well. The result would not be something I could evaluate. So what I'm going to have to do is use a trig identity. Remember chapter 5? Once again, dust off that old dusty memory. You remember this relationship. So we're going to keep that one in mind. And we're going to try to solve this for sine squared theta and this for cosine squared theta, and then plug into that equation. So if I divide the first one by 5, I get this. If I square both sides, I get this. So there's something I can plug in for sine squared theta. Thought you could forget all about those old identities, didn't you? Wrong. So on the second one, if I divide both sides by 3, I get this. If I square both sides, I get this. And then there's something I can plug in for cosine squared theta. So that result is going to look like this. Y squared over 25 plus x squared over 9 equals 1. And then if I rearrange those terms to put them in standard form, actually, that is in standard form, never mind, because the 25 is a bigger denominator. So anyway, there's our rectangular representation. What shape is this, Rowdy?
What shape?
Indeed. Yeah.
Oh,
Well, we've only discussed 4, so you got a 25% chance of guessing it.
right. It is a hyperbola.
You're close. Remember, hyperbolas have a negative squared term. In this case, they're both positive, so what does that should be? No, parabola has only one term squared. Think about those standard form equations I threw at you.
We only got 2 more left.
We do.
Ellipse.
That's correct. So, playing the odds. Do you see why it's an ellipse? Looks just like that standard form equation for an ellipse, and it's elongated along which axis, Mason?
Y-axis?
Indeed, it's stretched out this way. It'll be 5 units in its major axis from the center to the vertex, so a total of 10 units along its entire major axis, et cetera, et cetera.
Did you say the x-axis?
The y.
The y-axis.
Y is the major because it has the bigger denominator. One of those little 100 things you have to remember to get a good grade on this test. If you forget that, you're going to miss a question or two. All right, so let's see, there was one more I thought was kind of interesting. Yeah, projectile motion. So the thing that parametric equations do very, very well is model projectile motion. So here are our 2 formulas, T times V sub 0 cosine theta, where theta is the initial angle of the projectile's motion, which it would immediately begin to be affected by this G force, which is what? Gravity, and that causes that slight downward. You could never throw something hard enough to escape the force of gravity. We have escaped the force of gravity a time or two, spacecraft and so on, but no human could produce that sort of thrust. I think it takes some 3 or 4 kilometers per second to escape Earth's gravity. With the sun, it's like 200 kilometers a second. I might be wrong with that, but I'm vaguely remembering that from a science show I watched once. Okay, football. Shane Leckler of the Oakland Raiders has a record career punting average of 46.47 yards. That's beast. Suppose that he kicked a ball with an initial velocity of v sub 0 of 26 yards per second and at an angle of 72 degrees. How far will the ball travel horizontally if he punts it with an initial height of 1 yard? So let's start populating our variables here. First of all, I see v sub 0 equals 26, and that's in yards per second. We need to think about our units here. Theta is 72 degrees. H sub 0, the initial height, is 1. That should be everything we need. So x equals t times 26 times cosine of 72 degrees, and y equals t times 26 times the sine of 72 degrees. But in the y direction, there's an additional force that comes to bear. As we discussed, it is gravity, so we need to write that term. Minus 1/2 gt squared plus 1. And you might wonder why I'm not plugging in g. Well, if I plugged in g in 32 feet per second, it'd be wrong. Why can't I use feet? At least at this step. What were the other measurements in?
Yards.
Indeed, so I got to be consistent with my units. You will screw up a problem if you're not. So I know G is 32 in feet, but there's 3 feet in the yard. So 32 feet per second squared is the force due to gravity. If I divide that by 3, it's now in yards per second squared. So 32 over 3 is what I need to put in there. And I'm not going to bother to simplify that any further because I feel like we've had enough mathematics for today. Maybe too much. All right, so let me give you your 2 brief assignments for these 2 sections. So this is for 7-4.
Numbers 3 and 4.
Yep, told you they'd be brief. You're welcome. And then
The only thing, but they may be brief, but so that short takes like 20 minutes.
well, accurate. There's one hard one in there.
It took 20 minutes because you did it, so it'll probably take about 3 times for it. It's not that bad, it's just playing it.
Well, the ones I chose, Colby, are they're like the first example where they give you the theta, so you don't have to go. You remember where I did cotangent 2 theta is a minus. Yeah, so both of these have the theta predefined, so you just plug the theta in. It'll be a little quicker as a consequence, so maybe more like 15, 20 minutes. I don't know. Anyway, that's it. Hope you guys have a great day and a great weekend, and hopefully I'll see you next week, but you never know. People talking some crazy stuff.
I don't know either.